Good evening, my dear JEE warriors. Welcome to the JEE Booster series for 2026. This is your none other than your physics master teacher, your Captain Shreyas. And like I said, just a couple of days back, in the JEE Booster series, I'm going to pick up those chapters which will help you secure a good percentile in the upcoming JEE Mains January attempt. And we will see the concept, the theory, more of it, because I had conducted a poll recently on the channel and had asked you what do you guys need. And many of you said, Sir, it's not just the problems, it's also the theory which you want to understand, and then the application part, and then some questions so that we get that confidence. This is exactly what this session is all about. So these are around 2.5 hours to 3.5 hour sessions. So roughly 3 hours you can take. We'll be starting now at 5:30 and going on till around 8, 8:15, 8:30, right? Hi, Rajikumar, Anup, Ibu, welcome, Arvinda, Luna, good evening, Krishna. Yes, and today what are we going to do? Like the thumbnail says, modern physics. So we'll try and complete as many topics as possible in this particular lecture, right from photons, photoelectric effect, atomic structure, atomic spectrum, nucleus, binding energy, and that fission and fusion, right? Reactions. So all of this in today's lecture. So you know the scope of the lecture. I'll be teaching a particular topic. Okay, all the theory slides you will see it's a very different way of teaching. Yeah, it's not the same regular way. I have some amazing content lined up for you today. So make sure you're liking the video. If you've forgotten, mark your attendance by liking it. And mainly subscribe to the Vedantu J English channel. It is very, very important for all of you. Okay. So I'll teach a topic, I'll explain it, and then we'll solve some questions. Okay. That's how we are going to go. All right. No, semiconductors is a separate unit. I'll be taking it up separately as a chapter because it's a very, very big chapter in itself. Good evening, Nanda. Rahul, like I said, around 3 hours. Good evening, Vijan. Sorry, Vajra. Hi, J aspirant. Like I said, semiconductors is a big unit in itself. Hi, Aditya. Hi, Silent Killer. Welcome, 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 everyone. Sir, I tested my patience. Oh, yeah, there were some things which I had to finish recording. So I was finishing up the recording because I know this lecture is going to take some time. Okay. So that was the reason why I had to reschedule the class. But yeah, I'm here. Don't worry. Shreyas Sir is not going anywhere. So let's start with photons. Then we'll go to photoelectric effect before moving to atoms part. Now, modern physics has a very heavy weightage. Please remember, because if you see the questions every year, especially in the last 5 years, the weightage of modern physics has been steadily increasing. So doing this chapter alone will fetch you easily bare minimum 3 questions, up to 6 questions also you can get. Okay, but that is very rare case, but typically you get around 3 to 4 questions. That's what I have seen. Yeah, some mixed questions can be there, that's why it goes up to 6, but other than that, 3 to 4 questions, which is like easily 12 marks for all of you. Now, we start with photons. Okay, what is a photon basically? I'll tell you in a simple way. Okay, now see, light was thought to be like a wave. Okay, like sound. When I'm talking, what is moving? Sound wave is going, right? It's the wave of the sound. You might have seen on a beach, there are ocean, sea waves which are going on that water surface. So those are sea waves. You have sound waves when you are talking or listening to something. Similarly, when you turn on the light, what is going is light wave. But then it was understood that everything in nature has dual personality disorder. That means, imagine Shreyas Sir at home is very nice, very silent, very obedient. Suddenly, when Shreyas Sir goes out, becomes very angry, becomes like one monkey only. So that is dual personality. At home, you are silent. Outside, you are behaving like one hooligan, one monkey you are behaving like. Same way, light also, it behaves like wave in certain occasions. Like, for example, refraction, diffraction. These are like wave-like behavior. But in certain places, light shows that it is a particle, dual nature. And I am showing that dual nature of light, which is basically the photon part. Getting my point? Yes. So photon is basically the particle nature of light. You can think of photon to be the particle behavior or particle nature of light. And when I say particle, it means what happens when a particle hits something? It will have some momentum, it will apply some force, right? So all those kind of things. So when a particle strikes something, it shows its presence. Same way, when the particle of light, which is photon, hits something, it will apply some force, it will have some momentum, it will apply some impulse. So that's how I know light behaves like particle. And there are experiments to show that also. Now, these photons are also basically packets of energy. See, light energy is coming from the sun, light energy is coming from the bulb, light energy is coming from the fire. That energy is not coming continuously. No, 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 no. It is coming like in packets. Tok, 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 like that. It is not coming continuously. It is coming in packets. It is coming in packets. Like, for example, you take a pipe in which water is coming out, you spray the water everywhere, it is continuous, versus you fill water balloons and then throw those water balloons onto people. So those are packets of energy versus continuous stream of energy. So that packet of energy is also that photon. It contains some energy. Tuck, 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 it comes. The photon's energy and momentum are also defined. We'll see the values. The mass also we'll talk about it. But there is some energy associated with this photon. And when it hits something, it interacts. It has its momentum being impulsed over that particular matter. These photons are very quick. Don't expect them to go very slowly. They move at the speed of light. They move at the speed of light. Very, very important. Also, let's talk about the momentum of the photon. How much is it? Now, the momentum of the photon is given by energy of the photon divided by speed of light or Planck's constant by lambda. Now, what are these numbers? We'll talk about it. But the interesting part before going ahead is that the mass of a photon is zero. Remember this line. Now, this is very important because you cannot write momentum is mass into velocity for a photon. This equation is not valid because photon is not a mass particle or not a matter particle. It is a massless particle. So keep this in mind. If it is a massless particle, I cannot multiply a number 0 with some velocity to get the momentum. That is invalid equation. So never ever use m into v. M into v is valid for electron, proton, alpha particle, atom, molecule, one block, one ball, basically matter, not for photons. Is this idea clear? You cannot use this equation. Okay. Now, I'll come to this slide later on, these remaining points. But remember, the momentum of a photon is given by h by lambda. Now, what is this h and what is this lambda? Obviously, when I say light had a wave-like behavior or a particle-like behavior, any wave that you have, what will it have? It will have a wavelength and it will also have a frequency. So that wavelength is nothing but lambda. And we all know that the speed of the wave is frequency multiplied by wavelength. And the speed of light is basically c, which I explained it over here, which is very, very large. The speed of light is basically 3 into 10 to the power 8 meters per second. Extremely large, very quick. And that's the speed at which these photons will move. So that speed of light is frequency multiplied by the wavelength. So if you divide this constant, that constant h is also called as the Planck constant. What is it called? It is also called as the Planck's constant. Keep that in mind. Now, what is the value of this constant? I will mention that right over here. This constant is nothing but 6.6 into 10 to the power minus 34 SI units. 6.6 into 10 to the power negative 34. So it's very, very small. Wavelength might be few millimeters, nanometers, etc. So you can see the momentum is also generally very, very small. C is speed of light. I have already mentioned that. E is nothing but the energy of the photon. So what is exactly that energy of the photon? That energy of the photon is hf or hc by lambda. Some books use nu as the symbol, but you should be comfortable with either of them. You can put h nu or hf. Anything is fine. H is the Planck constant which I just mentioned, 6.6 into 10 to the power negative 34. F is nothing but frequency. Since speed of light was f into lambda, f is c divided by lambda. F is nothing but c divided by lambda. That is the energy of a photon. That is the energy of a photon. Yes, what is the SI unit of H? Well, as you can see over here, energy of a photon is H into F. What is energy's unit? You only think and tell me. It is joule. H unit, I do not know. What is the unit of frequency? It is 1 by second. So if I want the unit of H, I just take seconds on the top. Joules into seconds becomes the unit of H. Joule second is the unit of H. Yeah, I hope this is clear. Yes, Naveen, there is an offer, and because of Children's Day, so you can check out the link in the description if you want. Yeah. Okay. Having said that, there is a shortcut way of finding energy of a photon. See, imagine if I tell you I have light of let's say frequency 10 raised to 3 hertz, some frequency. What is the energy of that photon? Then you will be like, okay, energy is nothing but hf, sir. Okay, h is nothing but 6.6 into 10 to the power minus 34. Frequency is 10 to the power 3. So we get the energy as 6.6 into 10 to the power minus 31. That much is the joules of energy for that photon whose frequency is 1 kilohertz or 10 to the power 3 hertz. Is that right? Now, the calculation is simple when frequency is given. And things were not very difficult. But imagine wavelength is given to you, some nanometers, some micrometers, some millimeters, whatever, and you have to figure out the energy. It becomes one headache. It becomes one headache. Like, for example, I will show it to you over here. Say the wavelength is given to be, Chumma, I'm taking some random number, say 300 nanometer. And if I want to find now the energy by our normal method, then it would be 6.6 into 10 to the power minus 34. Then you have to multiply it by C, which is 3 into 10 to the power 8. The whole thing divided by wavelength, which is 300 into 10 to the power minus 9. So all these numbers are there, all these calculations are there. Yeah, you can do it within 30 seconds, but still, I don't want to waste that 30 seconds. Is there a shortcut way? The answer is yes. The answer is yes. What you can do is, look at this formula, guys. Whenever the wavelength is in nanometers or in angstroms, remember this number 12400 or 1240. So if my wavelength is in nanometers, what I can do is I can just write 1240 divided by lambda, provided this wavelength is in nanometers, then the answer of the energy that I will get will be in electron volt. Electron volt is a small unit of energy, and I need that small unit because if you notice over here, for normal frequencies, this energy is very, very small. 10 to the power minus 31, guys. Such a small energy. So it's very difficult to put so many decimals. So we convert it into electron volt. So we generally write electron volt as the unit of energy for such small values of energy. How do I convert it into electron volt? Whatever answer I get, you just divide it by E. So 6.6 into 10 to the power minus 31. If you divide it by 1.6 into 10 to the power minus 19, the answer that you get is in electron volt. And simple way to remember why I have to divide it, because the value of E is exactly this 1.6 10 to the power minus 19 coulomb. So if you notice, this E and this E cancels, you get back this. So because you are dividing with 1.6 this power, you are also multiplying it with E. So anyways, it's the same thing, just the unit has changed, which makes it convenient, to solve or relate. Okay, so electron volt is a small unit of energy that we'll be referring to. So what happens, my dear warriors, whenever you have wavelength given and you generally do not like the energy in joules, rather electron volt, so we will use a simple trick based formula. Remember these numbers: 1240 by lambda if lambda is in nanometers, but if it is in Armstrong, what is an Armstrong? 10 to the power negative 10 meters. Nano is 10 to the power negative 9 meters. So if it is Armstrong, add one extra zero here on the top. If it is nanometers, just keep a single zero. As you can see in this question, it is in nanometers. So I will not like these calculations because first of all, this is in joules. And if I want to convert it into electron volt, I have to divide by 1.6 10 to the power minus 19 so that I get the answer in electron volt. I don't like it. So what I will do instead is I will write it as 1240 whole number divided by 300. The answer that I will get will be in electron volt directly. 0 cancels. 124 divided by 3 is how much roughly? How much is it roughly, guys? 4.1? Yeah, approximately I can say it is 4.1. Yes, it is 41. That extra zero is also there. So that's why 4.1. So 4.1 electron volt is our answer. Isn't this method simple with this specific trick for nanometers? Same thing you can also do for Armstrong. Say for example, they tell you, listen bro, your wavelength is, 20 Armstrong. Can you find the energy? Here is what I will do. Because it is Armstrong, 12400 and then divide it by 20. Okay, this zero cancels. 124 divided by 2, that is nothing but 62, and then one more zero was there, so that's why 620 electron volt. That will be the answer. Got it, everyone? Absolutely clear? Will I take all subjects of physics? What do you mean by all subjects? Physics is a subject, Frey. Yeah. All right. I'm so glad, Harshit, uh, Anish. Yes, I'm so glad that you are enjoying the Ekalavya test series. Very good. So, whenever you want to find the energy of a photon, it's simple. All you have to do is, either use HF or HC by lambda. Answer will be in joules. But if you want it in electron volt, use 1240 by lambda or 12400 divided by lambda. That will give you the answer. Clear? Very straightforward. Okay. Sir, you also said about momentum, na sir? You also said about momentum. Can you help me with the momentum calculation? Yes, why not? I will help you with the momentum calculation. Look at it. If imagine it is given to me that, let's say, the wavelength of a photon, let's say, is 330, let's say, nanometer. Can we find the momentum of that photon? The answer is yes. Let's try it out. Momentum of a photon formula is h by lambda or E by C. Better to use h by lambda because lambda is given to me. What is the value of h? 6.6 10 to the power negative 34. What is the value of lambda? Well, 330, but that is nano. Nano means 10 to the power 9, negative 9. Is that right? Okay. What we can do is, I see the number 33 and 66. I got an idea. I will write this as 66 into 10 to the power negative 35. The decimal I have swallowed in the power of 10. In here, I will take 33. I will swallow this 0. So it will become 10 to the power minus 8. 66 by 33 is the number 2. This minus 8 goes on the top, becomes plus 8. 35 plus 8, my dear students, that's 10 to the power minus 27. So this is kg meter per second because we are talking about momentum. As you can see, is extremely small. It's extremely small. Is that right, everyone? So that's how momentum can be calculated, and that's how energy also can be calculated in electron volt if wavelength is in nanometer. And similarly, you can, if frequency is given also, you can calculate by using HF formula. Are these formulas clear? Let's do one more application based question so that you guys get it. Imagine if it is given, if the momentum, imagine if it is given to me, if the momentum is, let's say, 10 to the power minus 25 kg meter per second. Can you find the energy of the photon? Can you find the energy of the photon? Yes, we can definitely find the energy of the photon, and I'll tell you how. We all know momentum is h by lambda. Momentum is h by lambda or E by C or E by C. So I feel over here we should use momentum is E divided by C, which will give me energy is momentum into speed of light. And what's the momentum? It is 10 to the power minus 25. Speed of light is 3 into 10 to the power 8. So we will get 3 into, this is plus 8, this is minus 25. So 25 and 8, if you subtract, guys, that's going to be negative 17. So 10 to the power minus 17 is what you are going to get as the energy, but this will be obviously in joules since we were sticking with SI units. So that is the answer. Yes, very good, Arvinda. Excellent day. Clear how to use the energy, momentum, speed of light, frequency, wavelength. All these things I have juggled around. If you are clear, give me a thumbs up, put a smiley or put a fire emoji so that I get that confirmation. And if you, had some doubts, maybe you can put it up in the comments also later on. Okay, something else which is there, you can just put it up in the comments. I will definitely reply. You'll see that we have been replying to all the comments out there. Great. Very good. Now, let's look at other things over here. Observe carefully, guys. I talked about mass is meaningless for a photon. So we never use mass into velocity. Now, the next thing is, the number of photons may not be conserved, but it is always that the momentum and the energy are always conserved. What the hell does it even mean? Okay, number of photons may not be conserved, but momentum and energy is conserved. I will give you a simple example. Imagine out here there is some atom. Okay, there is some atom, and in that some electrons are revolving in some orbits. Okay, the electrons are revolving in some orbits like this. What happens? One of the electron goes from some higher orbit to lower orbit. The electron is jumping from one orbit to other orbit. This is called excitation, de-excitation process, which we'll be talking about in atoms. But for now, just assume that the electron which is going, it gets bored and it falls into some other orbit. What happens in this process? The moment this happens, you will see that there will be a photon. There will be a photon which will be emitted, a photon, light particle which will come out. But what does a photon have, guys? Quickly tell me in the chat box. A photon has momentum. So because the momentum of the photon is this way, we all know that by conservation of momentum, just like if I was holding a gun and I shoot a bullet, it goes there, I will feel a recoil like this. Everybody agrees? Or if there is a cannon and it shoots a cannonball like this, dhamal, what will happen? The cannon will go behind. Yes or no? Same way, here also, you will see the moment photon, I shoot it, I will feel a recoil behind, and this atom will recoil. The atom will recoil. And why is it recoiling? To conserve the momentum. To conserve the momentum. Is this absolutely clear? So momentum is conserved. But sir, this photon was there inside the atom only, no sir? It was hiding only, no sir? Somewhere it was in that atom. With that electron, it was sticking and it was rotating with it. Bro, no. That photon was generated. It was created. So that's why I said photons may not be conserved. A new photon might appear anywhere. A new or the existing photon might be swallowed. It might be destroyed. There is no guarantee a photon will survive or might suddenly appear like a ghost and scare you. Yeah, that's possible. A photon might suddenly appear or it might disappear. There is no boundary or there is no, such limit on photons. But momentum and energy principles, they are universal. Whether it is photon, whether it is mass, whether it is atom, whether it is Shreyas Sir, whether it is Vedantu, whether it is you, whether it is Pandu, whether it is Champa, you have to follow momentum principle, energy principle. You cannot violate it. Got it? Yeah, very good. Excellent. So that is why I have mentioned these things, because you might see certain things like that. Like, say for example, you know, it's told that we have some mass whose mass is, let's say, 10 to the power minus maybe 30 kg. From here, one photon is coming. One photon is coming. One photon is coming whose whose wavelength whose wavelength is, let's say, 6.6 into 10 to the power minus 4 kg, sorry, what kg? Meters. This photon is, let's say, absorbed. This photon is, let's say, absorbed by this mass. After it is absorbed, photon is destroyed. Photon is gone, vanish. What will this mass do? It's like power, this mass was chilling. Thuk, one photon came and hit. It will start moving. It will start moving. So this mass begins to move with some velocity. And the question has come in JEE. What is the velocity of this mass? What is the velocity of this mass? Bro, it is simple. Momentum is conserved. Yes or no? Universal law. Nobody can go against it. Neither Pandu, nor Champa, nor Shreyas Sir. Okay. Who is having momentum here? Photon. So the momentum of the photon is the momentum of that particle, that mass which is there. Now look at the beauty of this equation. On the right hand side, it is a particle having some mass. So I will use m into v. It's a matter, it's a particle having some kg. So I can use m into v. I will not use h by lambda. But on the LHS, it is not a particle, it is a photon. Photon, I cannot say m into v, it is massless. So I have to use h by lambda. So one equation with two different formulas for momentum. For photon, it is h by lambda. For particle, it is m into v. So, moving this around or just solving this, you will get the answer. For h is 6.6, 10 to the power minus 34, whole thing divided by lambda. What is lambda? 6.6 into 10 to the power, what's it? Minus 4. Okay, what is mass? What is mass? 10 to the power minus 30. What is velocity? I don't know. I have to find that out. Oh my God. What is happening? 6.6, 6.6 cancelled. Minus 4 cancelled. What is remaining? 10 to the power minus 30. Oh my God, 10 to the power minus 30. You are gone. Minus 30 gone. V is 1 meter per second. So this particle will go at 1 meter per second. We got it. Amazing. Amazing. Is that clear? Anish, Sigma batch is continuing, man. I think today, whosoever, maths and chemistry or maths and physics, whatever is there is going on. So please attend the class. Don't miss any class. Yeah, you have to attend all the classes in Sigma. You cannot miss one class here, one class there. Oh, no, don't do that. Proper planning is there in Sigma. Okay, cool, very good. So, sir, I understood photon, sir. Very clear concept is super duper, sir. Amazing, sir. So, we were also talking about before this, and okay, energy is done, wavelength, photons, everything is done, momentum, energy. Okay, done, done, done. Okay, now let us go to the next concept. But before that, there could be, say, a question like this. There could be, let's say, a question like this, and they tell you, can you find out how many photons are there in this beam of light, which has some intensity and it is coming through some area and all of that. This kind of question has also come. So let me talk about it because this is also crucial. There was a question like this in JEE where they tell, let's say there is some area, A, and through that area there are photons, photons coming. This is a beam of photons of wavelength lambda, which is coming, and intensity and intensity is I. Can you figure out? How many number of photons are passing? How many number of photons are passing per unit time? Per unit time through this, area. This is a very interesting question. Can be asked, has been asked in JEE, this model. So let me explain. First of all, what the hell is intensity? Intensity. Intensity is how much energy is flowing per unit time, per unit area. That's what intensity is all about. Okay. So what do you mean by this energy? Whatever is this energy is the energy of that light which is flowing through that area per unit time. Okay. But remember, this beam of light is made of photon. Each photon will have some energy. 2 electron volt, 2 electron volt, 2 electron volt, 2 electron volt. Just to my example I'm giving. So the total energy of that beam will be 2 plus 2 plus 2 plus 2 plus 2, 2, 2, 2, 2. How many ever photons are there? So can I say this energy is the number of photons multiplied by the energy of each single photon? The whole thing divided by obviously the time and divided by area, of course. So that is your I. Oh, I think I'm getting somewhere. So can I now say I is equal to N divided by time? I can just put T over here. Okay. So N by T into energy of that photon, the whole thing divided by area. Now I actually need this N by T, number of photons per unit time. So therefore, number of photons per unit time is I. A multiplies with it divided by energy of photon. But I know the formula of energy of photon, HF or hc by lambda. So I will use hc by lambda because lambda is given. So it is IA lambda by hc is number of photons per unit time. Done, dusted. Is that clear? Per unit time is asked. So not N by T is asked. Keep that in mind, per unit time. So if I value is given, A value is given, lambda is given, H is given, C is given, there is nothing big about this. It's not a big deal. So don't have to remember this formula. Don't remember it, guys. Just telling you how to solve the questions. Okay. So these kind of questions can also come. Keep in mind the idea of intensity. Intensity is how much energy is coming per unit time, per unit area. Everything is per. 2 times per is there. Okay. All right. Great. Now that we have understood what a photon is, I think it's good we talk about photoelectric effect. See, what did I tell you photon was when I started the lecture? I said photon is the particle of light. And what did I say particles do? They have momentum. They will interact with matter. They will apply force, impulse, blah, 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 blah. So imagine that photon is going. It interacts with matter. Matter means what? Atoms and molecules only. That's why. So that photon will come with full energy. It will hit the atom. Do you think it can break the nucleus? Do you think it can do something to the electron? Or do you think it will do something else only? Or so it will pass through that atom? What do you think? It will interact with the nucleus, it will interact with the electron, or it will just pass through that atom and say tata bye bye? Answer it in the chat box quickly. What do you think? Yeah. Arvinda, focus high weightage, but most of the 99% of the topics will be taught today. Yeah. Hmm. Yes. Yes, Pradyumna, the Sigma class is going on. If you are a Sigma student, you should be watching that class. Okay. Yeah. Already Sigma class is going on in full Josh, full energy. Everybody is, I think I can see more than 90% of the students are already attending every single class. Some people are, even though they are missing, they are watching the recording. I was just seeing the data, in the recorded format. Very good. Proud of all of it. Yeah. So what will happen? Do you think it can interact with the nucleus? No. Will it just pass through the atom? No, it will not pass. What happens is it will hit that electron, and when it hits that electron, all that energy gets transferred to the electron. That electron, because of that collision, will get one sudden impulse, like one sudden shock, jerk, and it will move out of or displace out of that orbit. But there is a catch. When that light particle photon is falling onto that electron gets a sudden jerk. If that photon has enough energy, then that electron will come outside of the atom. Else, if it is not enough, it might just jump within that atom and it will again be trapped within it. So, only if the photon has enough energy will that electron get out of the atom, else that electron just remains trapped. Do you guys agree with this statement? Do you guys agree with this statement? Yes or no? Quickly in the chat box. Very good. Yes, sir. I agree with this statement. So, my dear students, that's exactly what is photoelectric effect. The ejection of electrons from a material. The ejection of electrons from a material due to bombarding of photons on it is called as photoelectric effect. So, as you can see over here, the electrons are getting ejected due to bombarding of photons. So those light particles falling on a surface will throw out, eject electrons only if they are enough in energy. If that energy is not enough, those electrons will not get knocked out. So that required frequency or wavelength also depends on the material. Meaning, when light falls on that electron needs to be pulled out of that atom. That atom could be of sodium, could be of iron, could be of cadmium, could be of calcium, God knows. So every atom will have different energy which will be needed to suck out or knock out that electron. So that is why it is said the required minimal frequency. So I need some wavelength or some frequency of light which will throw that electron out will obviously depend on kind of material used over here. So as you can see, I can choose the light over here. It is falling on a surface. It is ejecting out electrons. So how much frequency or wavelength is needed depends on the material, because the material, the atom, decides how much is it holding on to electron. If it is holding the electron very tightly, it is difficult to remove the electron. So I will need more energetic light, meaning higher frequency or lower wavelength. Okay. So if it is not holding the electron very nicely, it is very loose, easily it can be knocked out, then a small frequency or a small energy of photon is also enough to chuck out or knock out that electron out of the atom. Hi Nishika, good evening. Very good. Now, having said that, let's go to the next thing. There is a particular wavelength, or I would say frequency below which you will not see any electron coming out. As you can notice over here, when the light falls, electrons are coming out. They are collected by another metallic plate. So what happens is, I have connected a wire between this metallic plate and the original metallic plate from which electrons are getting chucked out. So what happens is, the electrons which are thrown out are collected by over here by the anode, and because there is a wire connecting over here, the circuit gets completed. So as a result, what happens is, you will see the electrons start moving from this plate via the wire back to this plate, because if you just incident light and electrons continuously are chucked out, there will be no electrons only left. So those electrons need to be replenished. You need to restock them. So that restocking is happening because of the circuit being completed. So that is why I'm connecting this plate to this plate. So electrons are back, again light falls, again ejected, again goes back, again ejected. So that circuit is complete, and this current is then called as the photocurrent. What is it called? That is called as the photocurrent. So photocurrent, because photo means light. So because of light, electrons came out and it's making up that current. That's why photocurrent. Okay, or else we can just call it normal current. A normal current also flows when you connect a battery into a circuit. Okay. Now what happens is, if your frequency is not large, or let's say your wavelength is not small enough, because smaller the wavelength, higher the frequency, more energy. Keep this in mind. So when you have a small wavelength, then the frequency is large and even the energy is high. But when you have a large wavelength, the frequency is less and the energy is also less. Keep this in mind. So when you have a large wavelength, energy is less, it might not even emit a photon. That photon, not even emit an electron. If there is no emission of electron, nothing will reach on to the other side. If nothing reaches on to the other side, then what will happen? There will be no current only in the circuit. So that is why it said there might be no photocurrent even if there is much light falling on it. Even if bright light, dim light, anything falls, doesn't matter. Once the frequency is less or the wavelength is large, enough energy is not there, so photoelectric effect will not be there. But only after a particular wavelength, you will see the photoelectric effect will occur. So very, very important statement. Above a particular wavelength, when the wavelength is large, no current is observed even when light intensity is large. But once the wavelength is small enough or the frequency is large enough, then even if the light is dim, you will see the photocurrent will still be there. This is very, very important. Is that clear? Is that clear, everyone? Hi, Kumarant. Yeah. So once the frequency is large, doesn't matter. That photon will have enough energy to chuck out that electron. It will anyways chuck out that electron irrespective of how bright or dim the light is. But once the frequency is very small, the energy is also small, no current will come, and irrespective of how much light falls on it. That is what the logic is. Okay. Hi, Shetra. I'm very good. Hi, Kumarant. Yes, everyone. Yeah. This particular, one second. Where is it gone? This particular minimum energy of the photon which is needed, the minimum energy of that photon which is needed to chuck out that electron is also called as the work function. So the minimum energy of the photon which is required to eject that electron is called as the work function. It could be 3 electron volt, it could be 5 electron volt, it could be 7 electron volt, whatever that electron volt or joules is, that is the minimum energy required to chuck it out. The symbol for that is a phi, that symbol phi. What is the value of phi or that work function? That work function, like it is mentioned over here, is either you put h into f naught, h into f naught. F naught is that critical frequency, or frequency is c by lambda. So you can also write it as h c by lambda naught. What is it, lambda naught or f naught? What is that lambda naught or f naught, guys? Yes, that is called as your critical wavelength or threshold wavelength, and critical frequency or threshold frequency. So that frequency at which, or rather after which, the photoelectric effect will occur is called threshold frequency. And also the corresponding wavelength is called as the threshold wavelength. So you can use nu naught, or you can also use f naught. F, nu, both are fine symbols for frequency. So when your frequency is more than f naught, you can say photoelectric effect will occur. Photoelectric effect will occur, will occur. Keep this in mind. But the moment f is less than f naught, it will not occur. The photoelectric effect will not occur. So that is the threshold frequency, and the corresponding wavelength, the threshold wavelength. So h into f is the energy of the photon, that is the minimum energy required to knock it out. That is also called as the work function. Okay, very good. So I hope till this point everything is clear. Let's revise till now what we have done in photoelectric effect. Light will send packets of energy, tuck, 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 those are photons. Those packets will fall on a surface. They will interact with matter, basically electrons. Nucleus can't be touched because it's deep inside, it's very small, densely packed and everything. The electrons get knocked out, but only if the frequency of the light is above threshold. If it is below threshold, nothing will happen. No electron will come out. No current will also come in that circuit, even if the light is bright. But the moment the frequency is high, that's it. It will emit an electron irrespective of how dim the brightness is. And that minimum energy is called as the work function. Simple. Just to give you a simple example of threshold frequency and the work function, say I give you a simple example, the threshold wavelength, the threshold wavelength, of something is, let's say, or you have to find it out, how much is the threshold wavelength. If the work function is given to be, let's say, 3 electron volt, what is the threshold wavelength? That is the question. So let's see, how do we solve it? Straightforward. We know work function is nothing but hc by lambda. But this is in electron volt, and if I try to find the answer in nanometer, then I know I don't really have to substitute h value, c value and all of that. I can just write the answer as 1240 divided by lambda naught, but this lambda naught will be in nanometers and this work function should be in electron volt, which is actually the case. The work function is actually in 3 electron volt. hc by lambda is 1240. Lambda naught is what I do not know. So if you work this around, what you will get, lambda naught is 1240 whole thing divided by 3. How much will it be, guys? 124 divided by 3. Come on, guys. Roughly 410 nanometers approximately. So 410 nanometers is the threshold wavelength. Is that clear, everyone? Yeah. Yes, you will be studying atom also today. Yes, you will be studying atoms also today. Very good. Excellent. Perfect. Amazing, guys. Awesome. So, having said that, let's move ahead with the next concept coming up on your screen. Now, based on just this particular knowledge, that okay, a particle of light has hf energy or hc by lambda energy, and there is a minimum energy after which only electrons come out. So Einstein then thought Because obviously very brainy person. He thought, what will that electron do with that energy if more energy is there with that photon? Okay. See, I want some food. I am hungry. I need 20 laddus. But somebody gave me 30 laddus. Do you think I will eat 30 laddus? After eating 20 laddus, I'll be like, I am full. I don't want anything. So the 10 laddus, I will just give it away. Same way, imagine a photon comes with an energy of 30 electron volt. But to remove that electron, I need only 20 electron volt. So photon is having 30, electron needs only 20. So it will use up all the 20 electron volt to just come out. What will that 30 minus 20, which is 10 electron volt, do? That will be there with the electron in the form of kinetic energy, because now it will be moving. It will be moving. So it is there in the form of kinetic energy. Yes, very good. Excellent. Thermodynamics is going to be taught later on, not today, but it is a separate class. So, my dear students, that's what Einstein thought. When a photon interacts, it imparts its energy to the electron, and the electron can't absorb all that energy. It can only take a fraction of energy, and that, those fractions will be in the multiples of HF, 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 because whatever photons energy is there, only that energy will get transferred, and the remaining will then convert into kinetic energy. So that is why he said that the kinetic energy which comes out of that electron will be energy of the photon minus the work function. So this is nothing but HF minus work function. So I can rephrase this equation and I can write this as energy of whatever that photon is there after it falls will be work function plus the maximum kinetic energy, Ke max. Ke max. Energy of the photon, I can also write it as HF. I can also write it as hc by lambda. Work function, I can write it as HF naught, or I can also write it as hc by lambda naught. Maximum kinetic energy of the electron, I can also write it as half m maximum speed of the electron square. So all these things are valid. Okay, keep this in mind. Instead of energy of the photon, I can use any of these terms. Instead of work function, I can use any of these terms. Instead of kinetic energy, I can also use half mv square. So this plus this will give me this. That's it. That is the answer. Everybody clear about this particular phrase? Everyone understanding it? How this energy equation works? For this statement, Einstein won the Nobel Prize. Can you believe it? Yeah. For this particular statement, Einstein won the Nobel Prize in physics. Just giving the energy equation, the light's energy is used to suck it out, and the remaining goes in kinetic energy. And there are different ways of writing each particular term. So this is also called as the Einstein's equation of photoelectric effect, because Einstein gave it. Okay, great. So having said that, let us also now look at the graph. Yes, this particular graph of intensity of the light versus the current which flows in the circuit. Now look at this. If you observe carefully, more light falls, more photons will come, more electrons will be ejected, more electrons will flow in the circuit. The current registered in the circuit will also go proportionally higher. So that's exactly what this is talking about. If you plot the graph of the current, which is also called photocurrent, versus the light's intensity which is falling onto it, that is a linear relationship, proportional relationship. So photocurrent directly proportional to the intensity of the light. More current will come from more intense light. As simple as that. And there were some questions also based on that, which were asked in JEE. Like for example, if there is, let's say, a light source, if there is a light source and we have our photoelectric setup over here, and in this photoelectric setup, somebody is registering some current. Somebody is registering some current. And let's say the current which is being registered is 18 milliamperes at some distance, maybe let's say 2 meters. Now what happens is somebody will move this setup little bit far away, let's say at a distance of 4 meters. So in this case, what photocurrent will you get? That was the question. What photocurrent will you get if you move away from the source? Now, yes, the class notes will be provided. Everything for everyone, don't worry. Okay. I am teaching in the Sigma batch, man. Yes, I'm teaching in the Sigma batch. What are you saying? Like I said, Sigma batch, every subject will be taught by two teachers. You need full-fledged syllabus completion. Every day there are intense classes, two classes. So understand, we are taking help of Olympiad teachers in all of this. No other batch, crash course batch is giving you Olympiad teachers. The physics teacher with me, Nishan sir, is a Olympiad teacher. Okay, it's much more than JEE advanced level. I hope you understand that. Yeah. You tell me which other crash batch has such kind of teachers, because many crash batches have state level teachers, random teachers, teachers who are free, because all other good teachers are busy in big batches, right? Long term batches. Crash teachers means something only. Here I am spending so much just so that you guys get quality education. Okay, so you should be thankful. Okay, anyways, now coming back to the point of, sir, tell me, how do I solve this problem? If I move far away, how will the current get affected, sir? Maybe the light's intensity will change. And you know why light's intensity will change? Think like this. The light rays from this source will go in all possible directions everywhere. All possible directions everywhere. And think like this. Think like this. As you go far away, as you go far away, what happens? The light's intensity changes. When you're close, it is very intense. As you go far away, it becomes less intense. So the current will also change. So my dear students, over here also the same thing happens. Keep in mind, for a point source of light, the intensity of the light varies as the inverse ratio of the square of the distance from the source. Inverse ratio of the square of the distance from the source. As simple as that. And we also know intensity is proportional to the photocurrent. So indirectly, the photocurrent is inversely proportional to the square of the distance. So I can say I is inversely proportional to d square. Therefore, I2 by I1 will be d1 by d2 whole square. Therefore, new current I do not know. The old current I1 was 18 milliamperes. D1 and D2, first distance is 2, next distance is 4, so square it. 2 by 4 is half, half square is 1 by 4, so I2 by 18 is 1 by 4. So I2 is 18 by 4. Therefore, I2 will be 9 by 2, which is 4.5 milliamperes. So you got the answer. Okay. I hope this is absolutely clear. Everyone? Yes, Neo, like the batch has been distributed. Some days I will be teaching, some days Nishant sir will be teaching, some days Paul sir is teaching, some days Diksha ma'am is teaching, some days Namrata ma'am is teaching, some days Pramod sir is teaching. So I have told you all already, all of this, okay? In the launch video, yeah, everything has been told. Great. Anyways, so now that we understand it, sir, is there something interesting about the graphs of photoelectric effect that we can talk about? The answer is yes. So let's go over here. Yeah, this one, this particular graph. First graph we saw intensity versus current. The next graph that you are going to see is something called as the stopping potential on the graph, and current is there and the voltage is there. What the hell is this voltage, sir? Don't worry, I'll help you. See, just now I showed you the circuit over here, this particular circuit. This circuit, current was flowing. Let's say, as the current flows, I connect a battery. If I connect a battery, one of these two things will happen. Either the battery is in the direction of the current or it is against the direction of the current. If the battery is connected in the direction of the current, like in this case, electron is going like this, means current is going like this. So if the current is going in the anti-clockwise direction, so the battery negative will be here, positive will be here, exactly like this. That battery will help with the current. So what will happen? If you connect a battery, more current will flow. So, or if there was no battery, yes, there was some current which was flowing, but with the battery, more number of electrons will be pulled and you will see the current will increase. But then you might think, sir, if I connect more batteries, more voltage batteries, sir, more and more current will keep on flowing infinitely. The answer is there is a limit to it. Because think about it, even if you connect a very powerful battery, if there were 100 electrons emitted, maybe earlier 60 electrons were coming here, connecting this battery maybe made that 60 into 70, 70 into 80. So out of the 100 electrons, not all electrons will reach here because some electrons will collide, they will lose energy, they will go back only. Maybe some 50 electrons will reach here. You connect a battery so that 50 will become 60. You connect more powerful battery, 60 will become 80. You connect more powerful, it will become 100. But it can't become 110, no? Because if 100 electrons were coming out, maximum 100 electrons will reach. You cannot create new electrons. So there is a limit till which the current can increase no matter how powerful the battery is. That is why you notice that in this particular diagram which is there, when you connect a positive voltage, what is the meaning of positive voltage? You are helping, assisting the current. The current increases not beyond a limit. That is why there is a saturation current. Saturation current because there is a maximum value of the current, because there is a limit till which the electrons can reach onto the other side. Of all the electrons being emitted, all of them are reaching, then that current is saturated. You can't go more than that. Is that clear? What is the meaning of saturation? Okay. Now look at it. Look at it. Imagine if I now reverse the terminals of the battery. What will happen? The electron or the current which was going, now that current is going to be opposed by the battery. So what will happen? The current will reduce naturally because the battery is in the opposite direction of the current. So earlier 100 electrons were ejected, 50 were reaching onto the other side. Because the battery is opposite, it is stopping current. Maybe instead of 50 reaching here, 40 will reach. You apply more voltage in the reverse direction. Reverse voltage I call it. Instead of 40, it will become 30. If I increase the voltage further in the reverse direction, the 30 will become 10 and finally will become 0. The moment it becomes 0, I have stopped the current. So that battery's reverse voltage to stop that current is called stopping potential. So that battery's reverse voltage is then called as the stopping potential. So the negative potential for which the photo current is becoming 0 is called stopping potential V0 or Vs, whatever you want to call it. Is that clear? So you will see in the negative voltage, the current reduces, reduces, reduces till it finally becomes absolutely 0. Absolutely 0. Very good. Excellent. So you will see that the value of this stopping voltage is given by E into V naught because of electrostatics. What happens is when those electrons are being ejected out, the kinetic energy of those electrons will be swallowed by the electrical energy, electrical potential energy, electrical potential energy in the opposing direction, and electrical energy is given by how much charge is flowing multiplied by the potential difference, across which you are moving it. So the charge that I am moving is E, and the electron's charge is E, and that voltage difference is that stopping voltage, so V naught or Vs, whatever you want to call it. So that is why the kinetic energy of the electrons is also E into V naught, which I can add it in my photoelectric equation right over here. So instead of maximum kinetic energy or half m V max square, I can also put it as E into stopping potential, which is V naught or Vs. Very, very crucial. You can use this, this, or this. All three are the same thing. Stopping voltage is that voltage for which you will see the photocurrent stops, and that voltage is opposite to the flow of the current. So you're trying to minimize that current and finally make it zero. This is how I measure it. Is that clear, everyone? Perfect. Awesome. Awesome. Okay. Very good. Very good. GM, I think there was a video which would have been released on Children's Day, or it will release in some time. Just check that out and you will see all the details. Okay. Just check it out. It should be there on the channel. Now, very, very important thing over here regarding this. If now I change the, observe, if I now change the intensity of the light falling on it, what will happen? Think logically. More light falls, more current should come out. So that is why this graph will shift on the top. As the light's intensity increases, you can see yellow will become blue, blue will become red. Why? Because photocurrent should increase. So when the light intensity was I, current is I. When the intensity will become 2I, more current, 2I. 3I intensity, 3I current. So proportionally, the current will keep on increasing. But funny thing is, all these graphs on the reverse side, you will see the current will become zero somewhere. Their voltage to stop them is independent of the light's intensity. It only depends on the frequency of light and the nature of the material. So the stopping voltage will not be affected by the intensity of the light. And there is a very clear way of explaining it. If you use the Einstein's photoelectric equation, so energy of light is hf, work function is phi, and stopping voltage is V naught, so E into V naught. As you can see, none of these terms have intensity in that equation. Frequency is there, Planck is there, work function is there, charge is there. So that is why the stopping voltage is independent of the intensity. So saturation current increases with the intensity. Number of photoelectrons is proportional to the intensity. So the stopping potential is independent of the intensity. Very, very important. The stopping potential is independent of its intensity. The only thing which intensity decides is the current. The saturation current changes with intensity. That's all. Is that absolutely clear, everyone? Very good. Excellent. Now, there is also this graph which has to be plotted using the photoelectric equation. It's very simple to get it also. I'll just tell you how this equation also comes, and then we can see how that equation comes. That graph comes. See, we have HF is equal to work function plus E into V naught. Photoelectric equation. Move this around a little bit. So you will see E into V naught is nothing but HF minus work function. So therefore, stopping voltage is HF by E minus work function by E. Now look at this equation. It is exactly this equation over here. Stopping voltage is Planck constant by electron charge into the frequency minus work function by electron charge. This equation can be compared with Y is equal to mx plus C. Voltage is like Y, frequency is like X, slope is like H by E, constant is like minus phi by E. Equation of a straight line, Y is mx plus C. So that's why if somebody decides to plot a graph of the voltage versus the frequency, y-axis, x-axis, it will be a straight line, and the slope of voltage and frequency, the slope of that voltage and frequency will be h by e. H by E, H is Planck constant, E is the charge, and where it intersects the vertical axis will be negative, as you can see, and that point will be phi by E. The point will be phi by E, work function by E. Very, very important. Hi Santosh. Hi Red Ninja. Good evening. Vanakkam. Now, very interesting point about this. The slope is h by e. The slope of this graph, straight line graph, is h by e. The intercepting point on the vertical line is phi by e. The interesting point is, even if you change the intensity of light, even if you change the frequency of light, even if you use a different metal, irrespective of that, slope is a constant. H is a universal constant, E is the fundamental unit of charge, fundamental charge. So none of them can change. So no matter which material you choose, what intensity you choose, what frequency you choose, doesn't matter. Every time the slope will be same. What will change if you change the material is this work function. Different material will have different tendency to hold on to the electron. So to remove the electron, you will need different energy. So that's why they have different work function. That is why the point where they intersect on the vertical axis will naturally be different. Is that clear? The point where they intersect on the vertical line will also be different. So that is what is the key takeaway. Clear till this particular point over here? Yeah, this is very, very important, that this is constant for all material, but the y-intercept, as you can see, the y-intercept, it definitely depends on the material. It depends on the metal, It depends on the metal. And by the way, where it hits the horizontal line, right? This point, that is that minimum frequency at which the photoelectric effect will occur. This graph is drawn dotted because it is below, so you cannot have negative stopping voltage. So that is why this point is that point where the photoelectric effect will just begin. So that point on the x-axis where the graph intersects, that is nothing but your threshold frequency. Threshold frequency. Threshold frequency. Keep that in mind. Is that okay, everyone? Very good. Excellent. Maybe now it's a good time for all of us to solve some questions. Let's have a look at this particular question on your screen. The work function is given to us. The wavelength that can cause the electron emission is how much approximately? That is the question. Okay, let's solve this. Options are on the screen: 540, 310, 400, 220. I see first hint, unit of energy is in electron volt. The options are in nanometer. Immediately it rings a bell in my head. And what is that bell, guys? The energy, if it is in electron volt, is 1240 by wavelength, provided it is in nanometer. Now, this energy that we are talking about over here is nothing but the work function. Yes, the work function in electron volt, and this is none other than your threshold frequency wavelength. So that longest wavelength for which electron emission will occur, meaning we are talking about that limiting condition, critical wavelength, threshold wavelength. So this is nothing but lambda naught. So we can easily find it out. Phi is nothing but 4. 1240 is over here. lambda naught is not known. So lambda naught will be 1240 divided by 4. How much will it be? Yes, 310, but answer should be in nanometers. Hence, the correct answer is 310 nanometers. Is that absolutely clear, everyone? Very good. Deepan, awesome, awesome. Very good, Santosh, IT Bombay, perfecto. Very good, Vaishnavi. Hello, hi. Class 11th also we will be doing, don't worry. Excellent day. Moving on now to the next question on your screen, and here it is. The threshold frequency of a metal for photoelectric effect is F naught. When the light frequency is now 2F naught, the maximum speed is V1 and okay, all right. When the frequency of the light is now 5F naught, what is the maximum speed is given to be V2? Find the ratio of V1 by V2. Okay, let's analyze this. Question is find the ratio of V1 by V2. Let's remove the noise. I don't need the options. We can just solve the question. Light is falling onto a metal. The metal will allow photoelectric effect to happen because the only if the frequency is more than F naught. F naught is critical frequency. First time the light falling is of 2F naught. Second time the light falling is of 5F naught, different lights. So the speed of the electrons is also different, V1 and V2. Question is find that ratio. Okay, here is what we will do. First we'll write the general equation. What is the general equation? Energy of my photon is nothing but the work function plus the maximum kinetic energy. Everything is in terms of frequency. So energy of the photon will be hf. Work function will be hf naught. Kinetic energy will be half m v max square. Now let's look at the first set of data. When the speed is v1, then what is the frequency of the light? The frequency of the light is 2f naught. So for the first place, for the first situation, the frequency of the light is 2f naught. So I'll put h into 2 times of f naught, which is the energy of the light. Work function h into f naught, because it is clearly mentioned in the question, the threshold frequency is simply f naught. The maximum speed is already given, which is v1. So I'll put v1 square. I'll just put v1 square. Is this equation clear? Give me a thumbs up quickly in the chat box. Yes? No? Very good. Very good. Awesome. Very good. Chevuri, I have already replied to that comment before. You had put that comment in some video. It has already been replied. Check that reply to that comment. It has been mentioned. Okay, you guys ask the question, but don't read the replies. Okay, next thing over here is for the second situation, when the light's frequency is 5f naught, the new speed is v2. So imagine the energy of the photon will now be h into 5 times of f naught, that is the new frequency. Threshold wavelength, threshold frequency is still f naught only. So work function is just hf naught. New speed is v2. So instead of v max, I'm going to put v2 square. Okay. Now what do we do now? Observe this. If you see this equation, I can shift hf naught over here. So what I will get is 2 hf naught, 2 hf naught minus hf naught is half m v1 square, which is as good as saying 2 minus 1 is 1. So it is just hf naught is half m v1 square. Same logic I will apply over here. I shift this guy over this side. So from 5 hf naught, I'll be subtracting just hf naught. What is left is half m v2 square. 5 minus 1 is 4. So this will become 4 h f naught is half m V2 square. Now what to do? Observe this carefully. If I divide this with this, if I divide this with this, HF naught cancels. I'll be left with 1 by 4. Half m cancels. I'll be left with V1 square by V2 square. What is this telling me? If I just take V1 by V2, I will have to take root of 1 by 4. Root of 1 by 4 means 1 by 2. They have asked exactly that ratio. What is V1 by V2? So it will be in the ratio of 1 is to 2. That's it. That is the answer. 1 is to 2 is the answer. Is that clear? Very good, Deepan. Excellent. Hi, Kiyotaka. Good evening, everyone. I was talking exactly about that Sigma batch only, my dear. I mentioned that in your reply to that comment in YouTube only you have asked that. I've replied there. So check it out. Okay. Yes. And just some time back only somebody asked the same doubt. I replied to that also. That, my dear, yes, two teachers are going to teach. One day one subject, one day other subject. I mean, one day another teacher, and it will continue. But the topics are separate. So whatever topic I will teach, Nishant sir will not teach, obviously, or else you will get confused. And we are making that plan and giving it to you on the schedule only. You will be seeing everything. It's all there. Okay, you don't have to break your head. Just attend every day. Your job is every day there are two classes, you have to attend it. You don't break your head. So today if you teach, tomorrow will you teach? It's there on the schedule. It is all there. Don't have to worry. Okay, very good. Cool. So having said that, let's go to the next question coming up on your screen. Here it is. Three different colors are used in photoelectric setup with same light's intensity. Then the current versus voltage graph will be three different colors are used. What will happen if the intensity is same? If, look at this, same intensity means same saturation current. Same saturation current will be there. Here, the saturation currents are different. Saturation currents are different. Saturation current is same, saturation current is same. So, yes, my dear students, automatically option A and option B gets ruled out. It has to be C or D, but I think there was some printing mistake over here. So, C and D options are similar except for the order. Ignore that order PQR. So there must be some printing mistake over here. So maybe these points might be the same or different. I think that is what the only issue is. So if I just ignore for now the D option, my dear students, if I just ignore for now the D option because it looks very similar, you will notice the correct answer to this particular question will be option C, because different colors means different energy. Different energy means different stopping voltage. Yeah. So different stopping voltage. So the graph will end at three different locations. Is that clear, everyone? Very good. Amazing. Amazing. Awesome. Awesome. Now we'll start with atomic structure in 5 to 10 minutes. Let me take a 5 to 10 minutes break, okay, because it's a marathon. Just will return in 5 to 10 minutes, okay? Just give me some time. We'll come back. Welcome back, everyone. Yes, time to begin with atomic structure, right? Everybody ready? Yes, Prithija, everyone, Cheburi, Deepan, welcome, Kyotika, welcome. Yes, let's begin. J Aspirate, yes, GM, everything for everyone. Red, Santosh, Vaishnavi, Shankareshwaran. All right, let's begin. I hope I'm audible and visible to all of you. Okay. Now, in this particular chapter, there are certain models which are there of atoms, which you should know theoretically, and the rest is main thing, which is Bohr's model of atom. So let's start with the basic models which are there. The first thing that you should know is where is it? Okay, actually Thomson's model they have not. I'll just make that slide over here. Yeah, the first model that you should know is the Thomson's model. Thomson's model of atom. Everybody thought of the atom to look in a different way. As more and more experiments came, then they understood actually how atoms look like or what is there inside an atom. There were some problems in some theory or some visualizations. They overcame it with the next and next model. The first basic model was by Dalton. But Dalton model was very, very basic. Laddu atom is neutral and all of that. But main model started with Thomson, where Thomson said that actually the atom is having uniform distribution of positive charge. It's like a cake or a watermelon. Okay, so there is positive charge which is distributed, positive distribution of charge, positive distribution of charge, and if it's a positive distribution of charge, then the positive will repel and they will fly out everywhere. So what happens is there is negative charge not just at the center everywhere, but it is like a point, like one negative here, one negative here, one negative here, one negative here, like this. So he said there are negative, electrons, negative electrons which are embedded in that region of positivity. And what happens is these electrons hold that positive charge, and same way these electrons are also held by the positive charge. Anywhere you go, the positivity is there everywhere, so those positive charges will apply forces and balance it out. Same way, the electrons are spread out everywhere, they apply electrical forces and balance out the forces on the positive charge. So the Thomson's model actually led to the discovery of electron. The discovery of electron. Okay, now this was a basic model which talked about how electrons are like seeds of a watermelon, and the watermelon itself is the positive charge. And just like the seeds can be removed easily, you apply some force, the seeds get come out. Same way, the electrons also get knocked out. That's what Thomson's idea was. Thomson could not explain many more things, and that is what Rutherford tried to explain them. So Rutherford's model was that the atom is not evenly distributed with positive charge, rather it is concentrated at the center, and Rutherford was the person whose model led to the discovery of nucleus. Discovery of nucleus. This can come also in match the following, by the way. Scientists name their discoveries, inventions, etc. Correct. So he said that the positive charge is concentrated at a very small space that is called nucleus, and that space also has most of the mass of the atom. So if the atom's mass is, let's say, 100 units, 98 or 99 units were here of mass, and remaining 1 or 2 units is there in the electron, and that electron is circling around that positive charge. In the Thomson's model, the electrons were at rest and all of that, but in Rutherford's model, the electrons are actually revolving around the nucleus. And why it is revolving? Because this electric force between the nucleus and the electron is like that gravitational force between the earth and the satellite, which causes the revolution. So this electric force was giving that acceleration towards the center, and that's how the electron is revolving in a circular motion, because the electric force is like the centripetal force. That is what Rutherford said. atom is mainly empty, positive charge is concentrated, and yes, the atom is neutral, electric force behaves like a centripetal force, causing the electron to revolve in circular orbits. But how did he make this discovery? He was able to make this discovery because of alpha ray scattering experiment. What is alpha particle? Alpha particle means helium is there, right? So helium double plus. Helium double plus. Basically, you take out both the electrons from the helium atom. So there are only 2 protons and 2 neutrons. It's decently heavy and it is a positive ion, doubly ionized. Now, such a big positive charge and also mass is there. What they did, they passed the double ionized helium nucleus, alpha particles basically, through a gold sheet. Gold is there, you have gold jewelry. So imagine a golden sheet is there. Now, gold is a big atom, heavy nucleus. They passed it. They found that most of these alpha particles were able to pass through the gold sheet. Why was it so? Because of the simple fact that the atom is mainly empty. So if a alpha particle came, it used to pass through the gap between the atom's nucleus and the electron, or between one atom and the next atom there is some gap. So it was easily able to pass through the gaps between the nucleus and the electrons. Okay, so that is the reason why you will see the alpha particles were able to go very easily on the other side. Very few times what used to happen is that this alpha particle used to come, it's a positive charge, while it is passing through the gap, it used to come very close to this nucleus, because nucleus means positive charge, alpha is also positive. So what will happen, as it comes close, it will face repulsion and used to move away from the nucleus. Very few times, 1 in a million chance or 1 in 1,000 chance, the alpha particle used to come very, very close to the nucleus. So because of which it faced lot of repulsion and it used to turn back almost like 180 degrees. But that was very, very rare, because so many alpha particles will be going. Most of them will pass through the empty spaces in that atom. Very few times they will come close to the nucleus and get deflected, but very, 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 very few times they will get deflected completely. So that is why he was able to detect how much is the deflection, and that deflection was very much less, for most of the alpha particles. Most of them just passed as it is because it was relatively empty. A very tiny fraction got deflected by a very large angle. That was his observation. The size of the nucleus is very small as compared to the atom. The electrons revolve around the nucleus in circular paths. That is the conclusion. And what he observed, most of the space is empty. Positive charge is occupied by a very small volume inside the atom. And this charge in the center is called as the nucleus, which was the discovery of the nucleus. And most of the mass is inside the nucleus, not with the electrons. Electrons are negligible mass. Is that okay? All right. Sir, we know gold atom is too much small. How do we know alpha particle which is smaller than that will be visible even though the screen is present black? See, gold, they knew Mendeleev's periodic table and all that they had discovered, no, by that time. So they knew that gold is a heavy atom, a bigger atomic number. So they will have more orbits, or the electrons will be going more away from that, particular nucleus. So they had that idea long time back. Okay, great. Moving ahead, after this is the concept of closest distance of approach between the alpha particle and the nucleus. This is very interesting. So there are very few alpha particles which go head on to the nucleus and they encounter the nucleus. They can't pass through the nucleus because it's a positive charge. So they will repel. So what happens, as this alpha particles come close, they will lose their kinetic energy and they will lose it until it stops and makes a U-turn and returns. Once they stop, that point to the nucleus is the closest distance between the nucleus and the charges. That is also called as the closest distance of approach. So the minimum distance beyond which alpha particle cannot approach, no matter what you do, the alpha particle can't come that close. That is the minimum distance of approach, and that can be calculated by simple formula. Whatever kinetic energy is there with the alpha particle will completely go into the potential energy between the alpha particle and the nucleus. So this was our alpha particle and this was our nucleus. So all that kinetic energy will convert into potential energy. What is the kinetic energy? Half mass into speed square, speed with which it was moving. What is the potential energy? As soon as it reaches some distance, this is the closest distance. So maybe it reaches till here, and this particular distance, as you can see, is R, which is the closest distance. Remember, electrical potential energy formula is Coulomb constant, charge 1, charge 2 divided by distance. So what is Coulomb constant? K value, we all know. Coulomb constant 9 into 10 to the power 9. Coulomb's constant, standard value. Charge 1, charge 2. What is the charge 1? Right over here. ZE. What is E? E is the electron charge. What is Z? Atomic number. How many protons are there inside the gold nucleus or whatever nucleus? That many protons into 1.6 10 to the power minus 19. Why 2E? Because alpha particle is doubly positive. So that's why 2E. Q1, Q2 divided by R. What is R? R is the closest approach, because after this it will stop and it will return. So at this point it stops before returning back. So it will just go back the same way. Is that clear? Absolutely. Everyone understood? Yes, perfect. Amazing, amazing. So let's look at some questions coming up on your screen. And here it is. It was asked in JEE Mains. Let's see if we can get it. In the Rutherford's experiment, alpha particles are scattered from a nucleus as shown. Out of the 4 paths, which path is not possible? Well. Some alpha particle will come, it sees the nucleus, positive repulsion, it will go like that. A is possible. Alpha particle will come, will see the nucleus directly in front, will stop and return. That is also possible. C, alpha particle is coming close to the nucleus and gets attracted. How positive attract positive? It will repel, no? So I don't think C is possible. D is possible because it is repelling from it. So hence, the correct answer is option C. Is that clear, everyone? Very good. Awesome. Yes, it is linked with chemistry also. Very good. Let's move to the next one. In the pudding model or the watermelon model, pudding means cake. In the cake, you have cherry, right? You all have tasted birthday cake. In birthday cake, sometimes they put cherry. So that cake was like the positive charge. The cherry in that cake was the negative charge. Cake pudding model, whatever, cherry pudding model, or you can also call it watermelon seed model. It's the same thing, Thomson's model. The electric force on the embedded means it is trapped inside, it is embedded inside it. What is the electric force? What is the answer? Ravi, yes, you will be getting the notes, don't worry. Yes, Subhalakshmi, you will be getting the notes after the session is over, but there is no point reading the notes, let me be frank, unless you attend the class. If you attend the class, you will make sense out of the notes, else you'll be like, what is happening? I know that everybody is loving the notes, sir. What questions, sir? I loved the slides, sir. Sir, I loved the content, sir. Don't worry, you are going to get it. But watch, listen, because likewise, so on the Google also everything is there. You will get the notes, but watch the class. Yes, the answer is 0 because wherever the electrons are there, they will be pulled by positive charge from every side. Net force is 0. Wherever the positive charge is there, they will be pulled by electrons from all the sides and the net force will be 0. So the forces get balanced out and that's what it is. Very good. Awesome. Yeah, the notes you will get it in the description box by tomorrow. Not today, by tomorrow. Is that okay? Yeah. Very good. Awesome. Perfect. Let's go to the next question coming up on your screen and I'll show you how to solve this. There is an alpha particle of some energy. It is scattered by 180 degrees by some uranium nucleus. The distance of closest approach is of how much Armstrong or centimeters or meters, whatever it is. This was asked long time back, 2004, but this is still relevant because it also came recently in 24-25. Again, the same logic, guys. Closest distance of approach. So, closest distance of approach, what's the formula? Kinetic energy is the potential energy. Kinetic energy is half mv square. Potential energy is Coulomb constant Q1, Q2 by R. Coulomb constant we know. Uranium, we know Z. This E value also I know. R, I do not know. Mass and V, that also I don't know. But instead of mass and velocity, they have given something else. What have they given? Alpha particles kinetic energy they have given. What can you do with the alpha particles kinetic energy? Think about it. From kinetic energy, we can this 5 mega electron volts. I don't have to break my head. This half m v square itself is 5 mega electron volt. 5 mega. Mega means 10 to the power 6. Electron means 1.6. 10 to the power minus 19. Yeah. So this many joules of energy is there with the alpha particle. Kinetic energy of alpha particle. This kinetic energy of alpha particle will be the potential energy, which is K Q1 Q2 divided by R. So this will be equal to 9 into 10 to the power 9 Q1 Q2 divided by R. That's all. So everything will be known except for R. Except for R. That's what you will see. Look at it. Left hand side, like I said, 5 mega electron volt, 5 mega electron volt. So 5 into 10 to the power 6 into E. E is 1.6 10 to the power minus 19. This is 9 into 10 to the power 9, which is the value of K. 9 into 10 to the power 9. Q1, Q2. Well, the charge on a uranium nucleus is 92. So that is something which you should know. This is 92 into electron charge, which is 92 E, you can say. And the charge 2 will be 2E because that's the charge on the alpha particle, double charge. That's it. So that's exactly what they have done over here. Solving it, you get the answer as 5.3 10 to the power negative 12 centimeter. That's the answer that you get. Hence, the answer will be 10 to the power minus 12 centimeters. Order they have asked. They have not asked the exact value. The closest order. Order means the power of 10. That's all. Cool. Awesome. Awesome. Pritija, where are you replying? I don't know which platform. I tried searching. I did not get any message. I'm not sure by which account you are messaging, where you are messaging. Okay. Class 11, dual nature of atom, radiation. Radiation chapter, I'll be doing it later on, or else you can even search for it on our channel. It is there here only. If you just search for heat transfer, you will get it. I've done it before. See, heat transfer. Proper playlist is there, you will get it. Conduction is there, heat transfer by conduction, radiation. See, it is there. Lecture 2, heat transfer. Completely I have done. Even last year, Madan sir had done it. So same thing is there in row series or whether you want one shot marathon. Okay, cool. IIT Madras, awesome. Okay, yeah, great. Let's move to now the next main concept, which is the Bohr's model. Thomson told it is like watermelon. Rutherford told atom is empty and electrons are revolving. There was a problem with Rutherford. And the problem with Rutherford was that if electron is revolving, electron is a charge, and as it revolves, it accelerates because any uniform circular motion means accelerated motion. So they knew at that time that if you take a charge and you accelerate it, it loses energy. If it loses energy, what will happen? It will lose energy, lose energy, lose energy. It will fall into the nucleus. Blast will happen. That is not seen in the universe. You do not see atoms randomly exploding. So we won't be alive, no, in the first place. So that was a big flaw in Rutherford. How is it that these electrons, which are charges, are accelerating and still not releasing energy? That was convinced then by the next person, who is Bohr, the superhero, who told that don't worry, Actually, the electron should release energy in the normal situation, but there are very special situations in an atom where no energy gets released. Those places where no energy is released, those places where that electron revolves, they are called stable orbits. So only when that electron is in a stable orbit, only then that electron is stable, it does not release energy, the atom is stable, nothing falls into the nucleus. But by chance, the electron revolves in some non-permitted orbit, gone. It will lose energy, it will fall. But that never happens because the quantum mechanics, the electrons will only exist here or there. So there is a lot of, quantum science in that. Let's not go into that detail. But just now you need to know electron revolves around the nucleus in circular orbits. These orbits can only take special values in which electron does not radiate energy. Maxwell expected the energy to be radiated, lost, but in those special orbits, no radiation occurs. So those electrons are happy and stable. The reason why those electrons are stable in that stable orbits, that detail also we do not go, because it goes into some complex standing wave theory of matter waves, which we do not worry about right now. Okay, so in those special orbits, which are also called stationary orbits, the speciality is in those certain orbits. See, there could be, that electron could revolve here, could revolve here, could revolve here, could revolve here, but not all of them will work. Maybe out of that, this is okay, this is okay. Maybe this and this might not be okay. So this is a stable orbit, this is a stable orbit, but these are not. What is so special in these orbits? This is what is special. The angular momentum is integral multiple of h by 2 pi. Very, very important. The angular momentum L is an integral multiple of Planck constant divided by 2 times of pi. Only in those orbits the electron is stable. So L is nh by 2 pi. N is principal quantum number, any positive integer. Like for example, if n is 1, it is the k shell, the first orbit. N is 2, it is the lth shell. If n is 3, it is the mth shell. If n is 4, it is the nth shell. KLMN, the principal quantum number. Principal, this is your principal quantum, this is your principal quantum number. This is your principal quantum number. Keep this in mind. So angular momentum is nh by 2 pi. If you need the formula for angular momentum and you have forgotten, rotational motion, mass into velocity into radius, mvr or rmv, whatever you want to use. Generally better write in the correct way. So I'll just put r into mass into velocity. Yeah, one and the same thing, but there is a cross product, and cross product goes r cross mv. That's why I'm just sticking to the same order of alphabets, r cross mv or rmv. R is the radius, m is the mass of the electron, v is the speed of the electron. Is this absolutely clear? Everybody with me? Very good, very good, very good. Next. Bohr said, okay, now the electrons can be in this orbit. It can't be in this orbits. Only in those orbits where angular momentum is a multiple of h by 2 pi, it can exist. But he also went ahead and made one more claim, that the electrons can also shift the orbit. If it is right now revolving in the first orbit, it can suddenly get very high josh, motivation, and gets excited to some other orbit. Electron in the higher orbit, if there is a place below, vacancy below, then it can lose energy, lose hope, get demotivated, and it will fall into the lower orbit also. So both the things can happen. He said that when an electron jumps to the higher energy level, very, very important, when an electron jumps of higher energy, jumps to orbit of higher energy, or it jumps to an orbit of lower energy, then it will emit or it will absorb a photon. Very, very important. Very, very important. So, if there is an electron which is jumping to a lower orbit, then it will emit a photon. Then it will emit a photon. But the other way around, if an electron gets excited to a higher orbit, then it will be absorbing a photon. Then it will be absorbing a photon. Is this absolutely clear? So an electron jumping to a lower energy orbit will emit a photon. Electron getting excited, it has to absorb the energy. So it will absorb the photon and then go to the higher orbit. That is what he said. And he said that the exact difference between the energy of this orbit and this orbit, higher and low, is exactly equal to the energy of the photon. That's all. So if it jumps from one orbit to the another orbit, the difference of the energy of the orbits is exactly the energy of the photon being absorbed or emitted. That was the next thing which he said. Next important thing which he said was, this was same thing, electron can absorb energy and also jump to a lower energy from a higher orbit. The last thing which he said was right over here only, actually. The electron which is revolving in the circular orbits, it will experience electric force which will cause centripetal acceleration, and this force is electric in nature. So he said the electric force is mass of the electron into the centripetal acceleration. This centripetal acceleration is v square divided by the radius, and this electric force is Coulomb constant into nothing but the charge 1 into charge 2 divided by r square. Using this equation, we were able to figure out the radius, velocity and energy, every single detail of the electron. In what radius is that electron moving? We were able to get that. And it matched also. We were also able to predict the speed, frequency, time period, anything that you ask can just be figured out with this equation and this equation combined together. Because everything is known, Z, E, R, Z, E, K, V, and all of that. V and R are the only unknowns in this entire equation. So easily with two equations, two unknowns, it is solvable. And the answer that you get after solving it is as follows, right over here. Yeah, this was that force is equal to mv square by r. Solving this, here is what you get. Radius is some constant. Don't worry about what this number is. N square by z. Very, very important to remember. It is proportional to the square of the n and inversely proportional to z. So if I go from k to l, n will go from 1 to 2. So 1 becomes 2, square of 2 is 4, radius will become 4 times. If I go from hydrogen to helium, z will change from 1 to 2 in the denominator. So the radius will become half. So that's how radius depends on n value, the orbit number, and the nucleus proton number or atomic number, which is z. So that's how it is proportional to. You don't have to remember these constants, just forget it, just know the constant value is 0.529 Armstrong. If you know that, that is more than sufficient. That is more than sufficient. Is that okay? Yes, Anup, this is more than the high weightage. I would say this is like, I'm teaching like the entire chapter because some important chapters are there in your physics. So I'm teaching almost like the entire thing over here. Yeah. Now, very good question, sir. What about lithium 3 plus and all of that, or lithium 2 plus, lithium 2 plus and all? See, Bohr's model did one thing in a very sly and wicked manner. That Bohr, when he did all of this, and he said that yes, there is a force by the nucleus towards the center and all of that, he never ever calculated the force due to other electrons. It is a very smart move if you think about it, because the other electrons will also cause some repulsion, and that is very complex to calculate. So Bohr's model is only for single electron atoms. Bohr's model failed even when there were two electrons, that is helium. So we never discuss helium atom, we discuss helium plus atom. We never discuss lithium atom. In Bohr, we discuss lithium double plus because it has single electron, doubly ionized lithium. Getting my point, everyone? Yeah. All right. Very good. Amazing. Amazing. Now, having said this, so the radius is clear. So let's probably do a question on that. Here it is. Find the radius of lithium double plus ion in the ground state, assuming Bohr's model of atom to be valid. All the answers are in picometers. Let's try. We know that radius of any Bohr's model of atom is proportional to n square by z, and the constant of proportionality is 0.529 angstroms. Angstrom is 10 to the power minus 10 meters multiplied by n square by z. This thing is your constant. Okay, let's substitute everything. So 0.529 into 10 to the power minus 10. N is ground state. Ground means the first orbit. So N will be 1. So I'm just going to put 1 over here. Lithium, atomic number 3. So put just 3 over here. So 0.529 divided by 3 into 10 to the power minus 10. But if you remember, the options were in picometers. So I have an idea. I will write it as 52.9 into 10 to the power minus 12, whole thing divided by 3. Why did I do that? Because 10 to the power minus 12 is pico. So the answer will be in picometers, which is 52.9 divided by 3. Approximately, can you tell me what will be the answer? Come on, guys. Which of the options will match? Predict it quickly. Come on, predict it quickly, everyone. Very good. Some of you are already predicting it correctly. Yes. Very good. Very good. Very good. Come on, guys. Which answer is coming closest? Which answer is closest? C option. How, Ravi? C option 10? How is it C option, man? 52.9 divided by 3, man. 18 2s are 36, 18 3s are 54. So the closest answer is 18. So it is not exactly 18. Closest answer, I would say, is 18, not the exact one. So that's why the answer is option A, 18 picometers. Is that clear? Very good. Exactly. Very nice. Option A. Awesome. Let's go to the next one. Speed. Speed comes out to be value, constant, doesn't matter, into Z by N. So it is proportional to atomic number. So hydrogen becomes helium. Z will become from 1 to 2. Velocity will double. K becomes L. N will go from 1 to 2. But it is in the denominator. So velocity will become half. So velocity is proportional to Z by N. And the constant is 2.2 into 10 to the power 6. 2.18 is roughly 2.2, or 2.18 you can say, into 10 to the power 6. That is the constant which you should know. Usually constant is not needed, but still I have given it to you. Now, from this, let's see whether we can solve some question. Okay, here it is. The time period of revolution of an electron in its ground state is 1.6 10 to the power minus 16 seconds. The frequency of revolution of its electron in its first excited state is how much? Time period is given, frequency is asked, in its first excited state. So you need to be little bit careful about this. Okay. First of all, ground means n is equal to 1. Excited means 2, 3, 4, 5, 6. But the very first excitation will be n is equal to 2. So first one will be n is 2. Second time when it gets excited, n will be 3. Next excitation will be 4, and so on and so forth. Okay. Now, what do we do next? Let's figure out. Frequency and time, how is that got to do with this? If you take an electron, it revolves like this. in some radius. Well, the speed of it is circumference, which is 2 pi r, whole thing divided by the time period of revolution. So if you ask me, the time period is nothing but 2 pi r divided by v. But I know the radius is proportional to n n square, sorry. Radius is proportional to n square, and only n is changing, atom is same. So can I not write the radius as some constant multiplied by n square? Does that make sense instead of radius? And velocity, that's inversely proportional to n. So can I not write this as some new constant divided by n? Does that make sense to all of you? What I have just done over here? Because I know my velocity is inversely proportional to n. So some constant z is also same, so I'm not changing that. So that's all I have done. This is my time period. Oh, so you are saying, sir, 2 pi constant n square, n is there below. I can see this is nothing but 2 pi, some constants are there, constants are there, n square is there, this n also multiplies, so indirectly my time is proportional to the cube of n. My time of revolution is proportional to the cube of principal quantum number. Oh, perfect. Now in the first case they have given time period, second case they have asked the frequency. Not a big deal, we can easily figure it out. So if I write T1 by T2, that will be N1 by N2, the whole cube. The whole cube. First time the time period is already given, 1.6 into 10 to the power minus 16. 1 by T2, I do not know how much it is. N1 is 1, N2 is 2, whole cube. Perfect. What is 1 by time period? It is frequency. So this is the frequency in the next case into 1.6 10 to the power minus 16. This is equal to 1 by 2 cube, that means 1 by 8. Therefore, F2 will be 1 by 8 multiplied by 1 by this whole thing, 1.6 into 10 to the power minus 16. That will give me the answer. Okay, 10 to the power 16 will go on the top and 8 into 1.6. Do the math and see if you are getting the answer exactly what we have done. Yeah, 7.8 10 to the power 14. 7.8 10 to the power 14. 7.8 into 10 to the power 14. Obviously per second, that means it is hertz. That means it is hertz. Yes, that should be the answer. 7.8 into 10 to the power 14. Is this absolutely clear, my dear warriors? Everyone? Perfect? Awesome. Okay. Yeah. Answer is not possible means answer is possible, no? We just got the answer. Yeah. Telegram you have put up, is it Pritija? By what name? You said Ritik. I'll check it out. Okay. If I remember, that's what you said, no? Let me see again, because I was not able to find yesterday any message by the name of Ritik, but still again I will check. Okay. All right. So till now, what have we learned? That in a Bohr's model of atom, there are some specific criteria, some stable orbits where the force gives me the centripetal acceleration. They are stable and angular momentum is nh by 2 pi, and then energy difference is the energy of the photon being emitted or absorbed. The radius of such a orbit is proportional to n square by z, and the velocity of such a orbit is inversely proportional to n but directly proportional to z. That's what we have seen till now over here. Now let's go ahead. We can also figure out how much is the kinetic energy, potential energy, and all of that. Don't remember this. Just I'm telling you what is the answer, but don't remember it. I'll tell you why also. Kinetic energy is half m velocity squared. Similarly, why kinetic energy? Because the electron is going with some speed, so it has kinetic energy associated with it. That same electron is separated by the nucleus with some distance. So it has some electrical potential energy. K Q1 Q2 by R. K is 1 by 4 pi epsilon naught. Q1 is ZE. Second charge is negative E divided by R, which is the radius, which is also the distance. Why the minus sign has come? Because positive and negative charge will give me negative potential energy. Okay. So this is the potential energy. Don't by this. Again, I'm telling you, you'll understand why. If you add potential energy and kinetic energy, what is the sum of that kinetic and potential energy called? Answer it in the chat box quickly. What is that sum of potential and kinetic energy called, guys? Yes, Pritija, maybe. Yes, it is called mechanical energy or the total energy. Yes, so we will get the total energy of that electron. It has kinetic energy and the separation between positive and negative gives electrical energy. So I can find the total energy of the electron exactly, and that total energy, kinetic plus potential, comes out as 13.6 negative, total energy is negative, Z square by n square. Z square by n square. That is the energy of that electron with 13.6 as a constant, negative value. But the answer is in electron volt. The answer is in electron volt. Now, sir, you just told don't have to remember kinetic energy and potential energy. Why is it that, sir? Because kinetic is negative of, simply put, kinetic energy is just negative of the total energy. You can just remember this. And potential energy is just 2 times of the total energy. If you know this, that's it. Because total energy formula we already know. You don't even have to remember this one. Forget this. Now, I've already put it. It will be confusing. If you just know this equation, minus 13.6 Z square by n square electron volt, my job is done. I can find any energy in any orbit for any electron. For example, say I take the atom of helium in its second excited state, find kinetic energy, potential energy, and total energy. In its second excited state, what is its kinetic energy, potential energy, and total energy? Very, very straightforward. What will you do? There are some 11 chapters also which we'll be doing. Yeah, who is that? Ramya. I'll be doing some 11th standard chapters also, but some 12th also, because all are important. So I'll be taking it in priority order. All right. So first, let's start. Helium means my Z atomic number is 2. Second excited means N is nothing but 3. N is nothing but 3. What is the value of N? It is nothing but 3. Is that absolutely clear? Very good. Now, if you observe the total energy formula, what is it? The total energy formula, what is it, guys? It is negative 13.6 Z square by N square. Z is 2, so 2 square. N is 3, so 3 square. So this will be minus 13.6 into 4 divided by 9. How much is it coming out to be? Come on, my dear students, figure it out. 13.6 multiplied 4 times and then divided by 9. Yes, take 13.6 multiplied 4 times and then divided by 9. How many electron volts are you getting? Quickly let me know. Obviously, it will be less than 13. 4 by 9 is less than half. So less than, 7 for sure. Somewhere like 6 point or something you should get. Yeah, somewhere close to 6. 6 point something you should get. Just check this out. How much are you getting? 6 point. Come on, my dear students. Close enough to 6. Close enough to 6. You should be getting the answer as. Very good. Sharina saying 6. J aspirant, it won't be 9. Yeah. 6.04. Wow, very good. Calculated. 6.04 electron volt is the total energy. But that is not the end. The question says also find kinetic and potential. So the kinetic energy is negative of the total. That means it is negative of 6.04. So it will be positive 6.04 electron volt. That is your kinetic energy. But not just that, they also has potential energy. Potential energy is 2 times of the total energy. So 2 times of total is negative 6.04. 2 6 are 12. So minus 12.08 electron volt is my potential energy. So that's how you can find kinetic, potential, and total for any atom in any orbit. What formula did you use? We have just used energy is negative 13.6 z square by n square, and potential is double of total, kinetic is negative of total energy. Why is this total energy negative? The total energy is negative because it says that the electron is bound, it's constrained, it is stuck to that nucleus. Because when it is very, very far away, then the energy is zero because it has no interaction, no way of knowing what is there. So the electron is very far from the nucleus, zero energy. But when it comes close, it is negative, means it is bound to it. But if it had positive energy, it is not bound to it, it is free. It has more than what it would be at infinity or very far away point, because when it is far away, the energy is zero. If it has more than zero energy, that means even when it is far away, that energy is positive, so the electron is free to move. But only when the energy is negative, that electron is stuck, bound to the nucleus. That is why negative. Yeah, very good. Excellent. Moving ahead, moving ahead. Yeah, let's have a look at some of the questions coming up on your screen. Here it is. In the Bohr's model, electron moves in a circular orbit. Consider the orbiting electron to be circular current loop. The magnetic moment of the atom when the electron is the nth Bohr orbit is how much? You know what? This kind of questions can be done if you have the knowledge of magnetism. So they have combined. Why I'm taking this question is to show you how they can couple two chapters in one single chapter. So sometimes you might know modern physics properly, but you cannot proceed to solve this question because you do not know the idea of the magnetic moment. So the idea is when that electron revolves, it behaves like a current carrying loop, and that current carrying loop has a magnetic moment, north pole and south pole. So the answer to that is the magnetic moment by the angular momentum. The magnetic moment by the angular momentum is the charge divided by 2 times the mass. This formula anybody knows, they can easily solve. So what happens is my magnetic moment will become charge by 2m multiplied by angular momentum. The charge is electron charge. Angular momentum is n h by 2 pi by Bohr. So E by 2m nh by 2 pi. E by 2m nh by 2 pi. Where is it? Option C. Can you see that? Option number C exactly matches over there. So that is the correct answer. Very good. Proud of you if you guys got it. Yes. Awesome. Juggernaut, you only tell me if you have been watching from the beginning. Aren't you getting that full satisfaction? Yes, sir. You are explaining whatever I'm explaining very slowly, to the point, without nonsense, with examples, with the theory, with the concept, and also explaining you how to solve the question. What else you want at this point of time? Yeah. Yes, the chemistry class will be at 8:30. Yeah, the chemistry class will be at 8:30. Great. So, having said that, going back over here, where is that energy related thing? Now, this formula tells me the energy in different orbits. Is that right? Energy in different orbits. If you figure out how much energy is there in each orbit. If you figure out how much energy is there in every orbit of, let's say, hydrogen, 1, then 2, then 3, 4. I'm drawing some lines. This is the first orbit. This is the ground state, you can say. This is the ground state. This is the first excited state, n is equal to 2. This is n is equal to 3, which is the second excited state, and so on and so forth. Many lines will be there, and like this. And finally, you will reach a line, n is 4, 5, 6, 7, 8, 9, 10, 1000, 10,000, 1 lakh, 1 billion, and will become very large, which is tending to infinity. That is called as the free state. What is it called? It is free. Infinite orbit. South of the atom practically. It's free electron. So these are the energy levels. So what is the energy that you will get? When n is 1, I'm talking about hydrogen atom. Okay. I'm talking about hydrogen atom specifically. That means Z will be 1. So the first energy that you will get will be minus 13.6 Z square by N square. N is also 1. That will be minus 13.6. The next energy that you will get will be minus 13.6. Z is 1, N is 2. How much will this be? Come on, my dear warriors. Standard value. Come on. Oh, sorry, not chemistry, my bad, maths. Yeah, so sorry, not Diksha ma'am. Yeah, maths class is there. Yes, you are right. Okay. How much will it be, guys? Yeah, 13.6 divided by 4. Roughly, you should get it as 3.4 electron volt. Next, minus 13.6 Z square by N square. How much will it be? 13.6 divided by 9. How much will it be? 1.5. Yes, I know these values by heart, 1.51. So after that, when you reach infinity, it will become 0 electron volt. These few values at least you should know. As you can see, the values of the energy, actually I will put this over here. 13.6 Z square by N square, which is minus 13.6 electron volt. The values of these energies will keep on changing as you go on the top. Now, imagine if I have an electron here and I take it over here. How much energy will be needed to move it from here to here? Can you guess? I will need a photon. I will need a photon of how much energy? This is high, this is low. So it will be basically 13.6 minus 3.4. How much will it be? 10.2 electron volt energy I will need. I will need 10.2 electron volts of energy of photon. Only then this electron will jump over here. The reverse is also true. If an electron is here and it so happens that it jumps over here, then it will emit a photon of 10.2 electron volt. It will give out an electron of 10.2 electron volt. Very good. Excellent. Similarly, imagine, oh, by the way, you know what is this called? 10.2 electron volt in the hydrogen atom case. This is the minimum energy needed to excite the electron. That is why it is also called as the excitation energy. What do I call it? Excitation energy. But if I take this electron and I take it to infinity orbit, it's free. How much energy will I need? Minus 13.6 to 0, I will need 13.6 electron volt. I have knocked out that electron from the atom. I have ionized it. So this is then ionization energy. What is this called? Ionization energy. This is ionization energy. Whereas this over here was excitation energy. I'm exciting it. So excitation energy. Is the difference very, very clear, my dear warriors? What's the meaning of excitation energy? So I take it to the next immediate available orbit, that is excitation. I'm completely making it free. It is an ion. Negative is out, positive ion. So ionization energy. Sir, minus 10.2 or plus 10.2, it is always positive because you are taking the positive difference between these two numbers. Don't get confused between these negative signs. Don't break your head. This value and this value. What is the difference? Absolute difference. Absolute means mod. The difference will be 10.2. If you still get confused, here is what I'll do. The higher energy minus the lower energy. What is the higher energy? Higher energy is minus 3.4. Minus lower energy. What is the lower energy? Minus 13.6. Minus will be plus. So what is this looking like? 13.6 minus 3. So anyways, you are going to get 10.2. Okay, even if you consider the minus sign, still it will be 10.2 only. Is that absolutely clear? Very good, Sudarshan. Good, you asked it. Charina, I'm so glad you also made that mistake and you guys got the correct answer. Hi, Kritik. Good evening. My dear warriors, I don't think today we'll be able to do nucleus, and I think it is perfectly fine because whatever I'm doing it properly. Okay, I'll change the title, everything later on. That's not a big deal. The point is that I want you guys to learn anything that I teach properly. I don't want to just teach for the sake of teaching. Oh, I have 3 hours, so maths class is starting. Oh, I have to complete everything, blah blah. I don't do that. If I teach, I'll teach everything properly. Cool? And that is what Shreyas Sir does. Okay? Because, yeah, I want, if a question comes, see what is more important, covering whatever is planned or covering whatever is done in a proper way. Because if a question comes, I know on energy, you will be able to do it. If a question comes on radius of the electron, you will be able to do it. If a question comes on finding kinetic energy or finding some Rutherford's question comes or Thomson's model question comes, I know. Now you are visualizing. Thomson means that pudding is there, watermelon is there, that watermelon is that positive, sir. The seed is the negative, sir. Sir, closest distance of approach also I understood, sir. Why Bohr's model became famous also I know, sir. Rutherford failed because he thought the electron will just revolve normally, but Maxwell radiation is there, sir. Rutherford didn't think about it. So we now know everything. We know what is Bohr's model based on. I know it is based on 3 things only. Quantization, that is angular momentum is multiple of h by 2 pi. I know centripetal force is mv square by r, which is by electric force. And the last one, energy difference, is exactly the photons energy. Yeah, very good. Awesome, awesome. Now, having said this, we'll talk about spectrum. What's spectrum? Spectrum is basically a collection of wavelengths depending on the phenomena which happens, and every atom or molecule has a very unique collection of wavelengths. These set of wavelengths which it emits or absorbs are unique to the atom or molecule. What do I mean by this? If I ask you, now you are doing NTA registration, right? Sign. You'll say, yeah, sir, my sign is this. This is my sign, sir. Champa is like, sir, my sign is this, sir. Champa has a very unique sign. Pandu has a very unique signature. Nobody can match Pandu, nobody can match Champa. Same way an atom says, I have a very unique quality, which is my own signature, which is the spectrum, which is the collection of wavelength. If you take hydrogen atom or hydrogen atoms, they will give out a very unique set of wavelengths. Some 200 nanometers, 205 nanometers, 500 nanometers, like that. If you take helium, it is different. If you take lithium, it's different. If you take gold, it is different. If you take cadmium, it is different. If you take uranium, it is different. If you take iron, it is different. If you take aluminum, it is completely different. No two elements, no two compounds ever have the same set of frequency. Yeah, maybe one frequency might be same, but the other frequencies are different. The set of frequencies are always different. That is the critical point. So basically, we talk about atomic spectrum. The spectrum is nothing but the wavelengths, collection of electromagnetic wavelengths, and these wavelengths for every atom or molecule is very unique. That is very, very important. Now, there are two kinds of spectrum. One that you can have is emission spectrum or absorption spectrum. You don't have to go in this detail. You should know emission means if colors, wavelengths are coming out of it, of an atom, those are emission spectrum. But if light is sent through a material, some wavelengths will get absorbed, and the light passing through it will miss some of the wavelengths because some wavelengths will get absorbed, the remaining will pass through it. So out of the four wavelengths, maybe one will pass, sorry, one will absorb, three will pass. So that is absorption spectrum. That's the only difference. So you will see that you will, I'll just show it to you over here. Yeah. Absorption spectrum versus emission spectrum. This is very interesting. Look at it. You are sending many colors. Some colors are missing. That wavelengths which are missing, they correspond to those colors or wavelengths which are absorbed. That's why they are missing. You sent many colors through an atom. Few colors got absorbed. Those missing colors are dark. That is absorption spectrum. Emission spectrum will look exactly opposite of it, where you will see that a atom or atoms will emit certain wavelengths. One wavelength of this, one wavelength of this, one wavelength of this, one wavelength of this. That is your emission spectrum. The best part is, if you take emission spectrum and absorption spectrum, if you merge them together, you will get all the colors. You will get all the missing pieces of the puzzle and they perfectly match. Because think about it. Why should this happen? Why should this happen? Think about it. If an atom is absorbing a color, what will it do? It will excite that electron. The electron will get excited, jump up. After getting excited, it will again lose its motivation. It will jump back. It will emit exactly the same energy. So whatever it absorbs, whatever it misses in that absorption spectrum will again be emitted in the emission spectrum. Is that clear? That's why whatever is missing here will be exactly present over here. So they are both complementing each other. Is that clear, everyone? Very good. Very good. Yes. I'm so glad, Tamil Zlanda, that you are understanding everything. Okay? Awesome. Awesome. Is this very similar to atomic structure of class 11th? Exactly, man. It is very much similar to that. So this is basically absorption spectrum, how it works. So now what happens is we have these energy levels. We just spoke about it. Minus 13.6, minus 3.4, minus 1.1, minus 0.85, and it goes on. And it goes to 0 electron volt. These are the different energy levels. This is the ground state energy. These are the excited state energy. This is the free state energy. Now, if an electron jumps from here to here, that means it is getting de-excited. It will give out emission. So it will give out emission spectrum when an electron jumps below. But if an electron absorbs energy, that means a photon gets absorbed, that will create absorption spectrum. That is something which should be clear in your mind. So absorption spectrum, the photons are absorbed, so electrons get excited. In emission spectrum, the electrons get de-excited, so they emit the photons. Is this simple logic clear, everyone? Is this simple logic clear? Now, how much is that wavelength going to be? How much is that wavelength going to be? Simple logic is there. Whatever is the energy difference between this level and this level, this exact energy will be the energy of the photon. So this energy minus this energy is the energy of the photon. But sir, how much is this energy? How much is this energy? It will not always be minus 1.1, minus 3.4, minus 13.6. It could be helium, it could be lithium, N could be different. So I cannot just write E1 minus E2 is energy of photon, which is hc by lambda. And I have to substitute the value of h, substitute the value of c. I have to find E1, I have to find E2, it could be different atom. It's a headache for me. So this is good for starters, but not for my main course or deserts. So for that, we have substituted all the values and we get a special formula. And we get a special formula. What is that special formula? 1 by lambda, very important, is rz square 1 by n square minus 1 by m square. What is this? This is called as Rydberg's formula. Meaning, if you tell me the atom, hydrogen Z is 1, helium Z is 2, lithium Z is 3, like that. If you tell me the first orbit and the second orbit, where was it initially, where was it finally? N and M are those numbers, principal quantum numbers like 1, 2, 5, 2, 3, 5, 3, 10, whatever it could be. You put them over here. This is Rydberg's constant, who has a value of 1.01097. You can approximate it as 0.1. So into 10 to the power 7 per meter. This is the value which you'll put here. What you get is 1 by lambda. Lambda is the wavelength which is emitted or which is absorbed. Absorbed or emitted, that depends on which two orbits are involved in the electron transition. That's it. This is that formula. Is this clear now, everyone? Understood how this works? So the difference in the energy levels decides the energy of the photon. So if I know this orbit number, I can easily figure out the wavelength of the emission or the absorption spectrum. Very good. So having said that, keep in mind one thing. There are these names also given for these spectrums. So I'll put it over here. If the transitions are happening from any orbit to the first orbit, this kind of spectrum is called as the Lyman spectrum. What is it called? Lyman spectrum. Because for these transitions 2 to 1, 3 to 1, 4 to 1, these wavelengths are in ultraviolet range. So we have given it a particular name called as Lyman based on the person who discovered that this transition exists. If at all, the transitions happen between any other higher orbit to the second orbit, that is called as Balmer spectrum, Balmer series. They are in the visible range. Like 400, 700 nanometers based on the person who discovered it. Then what happens is you go to this range, any orbit to the third orbit, any orbit, but should be the third orbit. This is basically your Paschen series, which is reddish, in fact, so red that it becomes infrared in nature. So Lyman, Balmer, Paschen. Lyman is when it happens from any orbit to the first orbit. Balmer is when it happens from any other orbit higher than 2 to 2. Paschen is when it is happening between any higher orbit to the third orbit. There are more where the wavelengths are anyways here, like this one over here, even here. This is P fund bracket and all of that. Yeah, this is P fund bracket, Lyman, Balmer, Paschen, P fund bracket. These series are more infrared, deeper, darker infrared in nature. So this is your P fund and bracket series. These names and what numbers they correspond to, you should know with the colors. I've deliberately used blue so that you remember ultraviolet, Balmer whitish, meaning visible spectrum. Paschen is reddish, infrared. This is more infrared in nature. Is that clear, everyone? Okay. Now, if I ask you, hey, if you take question series, which of these transitions will give you biggest wavelength? Tell me quickly in the chat box. Come on. Yeah, come on, guys. I just come on, think and tell me. Yes, come on, guys. Everybody, which of them? Which of them will give me the biggest wavelength? Come on, think and tell. Shivani, P fund is the last. Yes, yes, P fund is the last. This is bracket actually. I just wrote it exactly opposite. This was P fund. So sorry. Yeah. Huh. Out of all the passion lines, which is the biggest wavelength? I'll give you an idea. Just go back over here. Just go back over here. This is the energy difference. It is hc by lambda. Biggest wavelength means this will be small. Energy difference will be small. Okay. Largest wavelength means smallest energy difference. So the largest wavelength will be over here. This energy difference is so large. Hc by lambda will be very large. So lambda will be small. So out of all these lines, this is the smallest wavelength. Is that clear? Same logic applies here. Out of all these lines, this transition from 3 to 2 will be the largest wavelength. Transition from infinity to 2 will be the smallest wavelength. Same logic over here. For Lyman, 2 to 1 will be the largest wavelength. From infinity to 1 will be the smallest wavelength. Reason? Hc by lambda is energy difference. So energy is inversely proportional to lambda. Keep that in mind. Energy is inversely proportional to the lambda. Yeah, perfect. Amazing, amazing. So keep all these things in mind. Okay, we have discussed about ionization energy and all of that before also. Okay, so I'll not repeat it. If you want, I'll just put it over here in this slide. Where did it go? It went somewhere. Here only. Yeah. Okay, cool. All right. So let's go ahead now to some questions coming up on your screen. Here it is. First question. Come on. Let's see if we can solve it. Everyone, figure this out. So these are the last set of questions which we'll be solving, guys, today. Okay. So after this maths class will start. Okay. Keep that in mind. Okay. The energy required to remove the electron from a singly ionized helium atom is 2.2 times the energy required to remove an electron from a helium atom. Okay. The total energy required to ionize the helium atom completely is how much? Okay. That is the question. Let's see. What do we do? Think about it. Okay. So the energy required is asked. Okay. To nucleus, we won't be able to do it today. Yeah. I'll just change the title later on because whatever we are doing it properly. The energy required to remove the electron from a singly ionized helium atom is 2.2 times the energy required to remove the electron from a helium atom. So if you want to remove the electron from a helium atom, what will that energy be? That will be ionization energy. So the ionization energy for helium is 2.2 times the energy required to remove the electron from 1 second. There is some mistake. I think there were supposed to be two atoms over here. So from a singly ionized helium atom, Uh, is they have given the same atom over here. I think there is a printing mistake, guys. Uh, we'll just skip it. Maybe there was a different question over here. I think it was supposedly something else. Anyways, we'll do the next question and then we'll probably come back to it in some other lecture where I will put the correct version, because it can't be helium and helium two times. It should have been hydrogen helium or helium hydrogen, something like that. Maybe it's a printing mistake. Anyways, the hydrogen atom makes a transition from 2 to 1 and it emits a photon. This photon strikes a doubly ionized lithium atom in an excited state and completely removes that electron. The least quantum number for the excited state of the ion in that process is how much? Okay. Say the photon is striking a lithium atom in the excited state and it is completely removing it. Which photon is striking? From the hydrogen atom which is transiting from 2 to 1. So if you consider the hydrogen atom from n is equal to 2 to n is equal to 1. So when the electron transits over here, the photon which is emitted, we can figure out that energy. Not a big deal, because in the ground state, the energy is minus 13.6 electron volt. Over here, it is minus 3.4 electron volt. So the energy of the photon will be 13.6 minus 3.4, which is 10.2 electron volt. So the photon's energy which is coming out of it is at least 10.2 electron volt. Till this point, absolutely clear? Till this point, absolutely clear, my dear students? Very good. Now, what is happening is this same photon is going and hitting a lithium atom. And in that lithium atom, the electron is already in the excited state. So maybe 1, 2, 3, some nth state it is there. And what happens is that electron gets completely knocked out. That means goes to the infinity state, gets completely ionized. So question is, what is this n so that this happens? It's very simple. Whatever this energy is there, that should be at least the energy difference over here. This energy difference, if you ask me, for that lithium ion, for that lithium atom, will be nothing but 13.6 z square by n square. Z is 3 square by n square. That will be the bare minimum energy difference between them, because at infinity it is 0 electron volt, at nth level it is 13.6 z square by n square. So the difference will be positive 13.6 3 square by n square, z square by n square. So this 10.2 should be more than nothing but 13.6 3 square divided by n square. So therefore n square should be more than 13.6 multiplied by 3 square by 10.2. Therefore n should be more than root of 3 square is 3 and root of 13.6 divided by 10.2. So n will be more than roughly how much? Now 13.6 and 10.2 will be 1 point something, guys. Root of this will be 1 point something. So 3 into 1 point something will be nothing but 3 point something. So n should be more than 3 point something, but n has to be an integer. So the smallest integer after 3 is nothing but the number 4. Hence 4 will be the correct answer. Got it? How we figured it out? Very interesting question. These kind of questions can also come in your JEE examination. Is that okay? Perfecto. Amazing, amazing, amazing. Let's go to the next question coming up on your screen based on the atomic spectrum, Lyman, Balmer, Paschen, bracket, P fund. Okay, so let's talk about that also. Here comes the question on your screen. If the series limit frequency of Lyman is mu L, then the series limit frequency for P fund series is how much? Okay, that's the question. Let's think about it. So I just gave you those lines just some time back. Where is it? Here. Yeah. Lyman, Balmer, Paschen, bracket, P fund. So Lyman is here, P fund is here. The question is, what is the limit of the series? What is the meaning of limit of the series, guys? That means the maximum possibility that you can get. So maximum possibility means from infinity. So whenever that question is on the limit of the series, that means we are talking from the transition from infinity. But since we are talking about Lyman first, Lyman is the first orbit, so infinity to 1. For P fund, the limit will be from infinity to Lyman, Balmer, Paschen, bracket, P fund. So 5. So this will be 5. So that is the first thing that you should be able to interpret. So of all these lines which we had, this is the first line, second line, third line, fourth line, fifth line, sixth line, 10th line, last line, that is the limit of it. Same thing over here for P fund or anything. First line, second line, third line, fourth line. Last line is the limit of that particular series. Okay, coming here. If you talk about Lyman series limit and the frequency is nu L, I will do like this. 1 by lambda of Lyman will be R into Z square. 1 by 1 square minus 1 by infinity square. So 1 by infinity is 0, 1 by 1 is 1. So it will just be RZ square is 1 by lambda. Now going to the next part of it, if you talk about P fund, 1 by wavelength of the P fund series will be R Rydberg constant Z square 1 by 5 square minus 1 by infinity square. Infinity inverse is 0. 1 by 5 square means R Z square by 25. That is 1 by lambda P. If you notice RZ square is here, so this will become 25 as it is, and I can write instead of RZ square 1 divided by, this is 1 divided by, what is RZ square? 1 divided by lambda of Lyman. Interesting. So 1 by lambda P is 25 lambda L. So hence I get lambda P is 25 times lambda of Lyman. Now comes the next part. Wavelength, frequency, and speed of light. We all know C is F into lambda. Therefore, lambda is speed by frequency. So use this concept over here. Lambda will be speed of light by frequency of P fund will be 25 times lambda of Lyman will be speed of light by frequency of Lyman. C and C will cancel. So what did we have to find? Limit of Fp, right? So 1 by Fp will be 25 by Fl. So Fp will be Fl divided by 25. This value is given to be nu L. So it will be nu L divided by 25, which is option number D. Which is option number D. Is that absolutely clear, my dear students? Everybody with me? Very good. Excellent. Perfect. This is how it should be, guys. This is how it should be. Is that clear? Yeah. So these are the kind of questions that you can get. I have solved many varieties of questions for all of you now. And we have done this thing in detail, these concepts of what is spectrum, what is this emission, what is this absorption, why this Rydberg constant, what is this N1, what is this N2. Still, if you have any doubt, please let me know. Okay, before we end the class. And because now your maths class will start. Okay. All right. But I hope you have enjoyed the class today. And don't worry, I'll be sharing the PDF also. And I'm again thanking all of you for, giving such nice comments on this series, the JEE, booster series for all of you. Thank you so much, guys, for those lovely comments. And I'm so glad that you all have accepted this challenge. I'm going to do everything in detail over here, like you saw today. No skipping concept. Whatever it is, I'm teaching you over here. Okay. All right. Obviously, we can't do derivations at this last moment. That is not important. I'm just teaching you the theory applying the formula, getting marks, and solving p-values. Cool. Thank you so much. Do not forget to leave a comment. I will show your comments next lecture again. And obviously, attend every single class for the next couple of days. Okay. Bye bye. Take care. Have a great time.